goes to psychologist or psychiatrist and have an assessment or complete the measure. How do we know actually that at that moment, in that particular day, there are not other factors that affect activity of the symptoms? In particular, some symptoms appear to be more dynamic over time and can be triggered by external environment. For example, a therapist can provoke some particular symptoms or the environment because somebody is listening to you, maybe that also. How do we know that? And that's a big question. So what people did over years and now doing, whatever we do in statistic, 80% of that or 85% of that is called classical test theory. That is what we rely on. And the classical test theory assess state and trait very simple. Just a correlation, merely correlation between test scores taken at two different occasions. Sometimes it's just two occasions and making conclusions based on that. But any scale, if you think about measuring depression, schizophrenia, or anxiety, has several items representing different symptoms of psychopathology. So how do we know if person goes and one symptom goes up and another goes down? The total score is not changing, right? It will be the same. So for us, actually, a level of participant is not changing. But what's happened, that somebody can get worse on some particular symptoms and we won't be able to notice that. And that is where a generalizability theory is coming from. So I will start introducing you slowly to that because you can see that our methods we are relying on may be less reliable than we think. So first of all, generalizability theory was developed by Cronbach. It's the same Cronbach who developed Cronbach's alpha. But his Cronbach's alpha coefficient, he was not happy with the Cronbach's alpha coefficient, seeing obvious limitations. Because reliability, how we measure it in psychology, we measure a particular pieces of reliability. We look at internal consistency, calling it reliability, Cronbach's alpha. We have external reliability, test-retest correlation, right? But there is no reliability which combines all of this. And there is also interaction between different aspects in the measurement. Like scale items may work differently at different time point. Participants may respond to scale also differently, depends on the time of the day, depends on the occasion of assessment as well. And also interaction between these factors. A particular participant may respond to specific items differently over time again. So for that reason, Cronbach was, of course, very happy developing generalizability theory. And he called that a liberation of reliability theory. But unfortunately, it was not very popular for many years because the reasons for that, it's very powerful method, but the reasons for that is lack of software appropriate to calculate covariance components because it's quite complex. And complexity of theory by itself. It is different than what we used to do in SPSS, in a classical test theory, because here you need to design a study, you need to actually to define your variables, which makes it a bit less user-friendly. Anyway, if you think about advantages it brings to us, then of course it was to study, it was to use, and it was to learn actually the software for doing that. Generally, generalizability theory, or what is called G theory in a statistical jargon, is an analytical technique used for psychometric measures. It's a lot of used in psychometric rating scales, performance tests, clinical examination, many different uses where you need a high precision. Also, what it does, essentially it combines all different types of reliability, what we can think about. And because it accounts for all different types of reliability in the measurement, it gives you a reliability coefficient which can tell you whether you can generalize your scores of the assessment taken on particular group of people, patients or students or general population, to the whole universe of people of the same, for example, from the same, speaking the same language or living in the same country. And this is a very strong statement, but it is testable and feasible. So this is a big advantage, because you replace all these small coefficients with one general coefficient, which can tell you much more. It can tell you whether you can generalize scores across different assessment occasions as well. So if you get a very high coefficient, you can go in every place and use your measurement instrument there, and you can trust the scores. You know that occasion will not have an effect on them. Not necessarily the case in many measures what we have, but this is an ideal case scenario. I talk about hypothetical, we have scales like that. Like personality measures are like this. Big Five, for example, you can take measurement in many different occasions. The error variance due to occasion is negligible. You will get very stable results. Okay, so it is very valuable to increase precision of assessment. Now I go to the next slide and show you what's happened in our statistics. Classical test theory, that is what we're using, assumes that observed score on any measurement instrument is a sum of true score, so true variance of what we are measuring, plus an error. And error is something where you throw everything in what you don't understand. Really, like it's an excuse for the difference between true variance and the total variance. We don't know what it is there. And you can see it's like a garbage container. You threw there everything. If we compare it to what we do with recycling, for example, in a classical test theory, if you have glass or you have a plastic, rest of food, anything, you throw everything in an error, it is an error variance. But there could be very useful things. For example, a personal state is a part of it. And that is very important. If we are assessing state, we need to extract that variance and recycle it. G theory has actually appreciate the variance across different sources. So here we have observed score exactly the same as in classical test theory, and we have a true variance, and then we have variance components for every source that influence the measurement. So of course, variance of person, error due to person, error due to item. Then we have error due to occasion, if you take a measurement at different occasions. And then you have all possible interactions. Person-item interaction, for example, if somebody respond to an item or people responding to an item differently, then you have person-occasion interaction. That means people respond to your test differently depending on occasion. Person-occasion interaction, by definition, is our state, because a person variance, is a trait. Is that what we possess? A tendency, consistent tendency to behave or produce the same behavior or the same thought pattern or the same characteristic over time. While occasion is something where people change. An interaction between your trait and the actual environment produces a state. This is very useful, but you can't see it if you look at classical test theory formula. It is a part of an error, and we don't know how big it is. Whether the whole error is due to state, and it can be, sometimes it is, or it is just a negligible part of it. So we have no idea. It's just an error. And we're happy with this until the certain time, until we need to be more precise. And these days with precision medicine, we want to know more, and error sources provide us very useful and important information. So then if we look at further, you can have also item-occasion interaction. What it suggests that some items may work differently at different occasions when people take the test. Like assessing, for example, schizophrenia symptoms at different occasions may produce different results because people will respond to environmental stimuli, and that will influence how they actually respond to the item as well. And then finally, you have a large source of error in many measurements is interaction between person, item, and occasion, suggesting that people respond to an item depending on occasion. So I think I covered everything in this very simple design. I'm not going to cover very complex designs today because I think this is the design what we used in psychology most of the time. If we use a psychometric scale, depression measure, anxiety measure, or schizophrenia measure, or personality assessment tools, we always deal with three major factors. We have a person, that is our object of assessment, what we are measuring. And then we have items in our assessment instrument. So questions, what we are asking or scoring, if we do it in a clinical setting. And then we take these measurements across different occasions. So this is a good example of what we do, and I will be using that today. So the main tool in generalizability theory to estimate variance components is analysis of variance. Our very popular ANOVA. But ANOVA here is used in a different way, because in a typical ANOVA, we try to reject null hypothesis, we try to look at variance, and we try to estimate p-values. Here, we are not interested in all of that. What we are interested, we try to estimate variance components as accurate as possible. And here I will need to introduce some jargon, because G-theory uses jargon. It is quite useful jargon because if you don't use it, you don't know what we are talking about, really. We need to define things. So something what is common for G-theory is called facet. Facet is actually any source of error variance or of variance in a measurement. Occasion is an example of facet. Item is an example of facet. And we have something which is called object of measurement. Normally in psychology, it refers to a person, because we usually measure people, patients or students or general population, but it can be, it's not necessarily should be human, it can be anything. So object of measurement can be items. If you develop psychometric instrument and you want to investigate items, items would be your object of measurement. And persons will be a source of error. So you can actually turn it the way you like, depending on what you want to measure. So in our case, what we do, we measure persons. So for us, if we measure persons, person is object of measurement, and items and occasions are facets. And then we have, they also called facets of generalization, because if you have facets and you estimate your reliability, you want to generalize across these facets. For example, we want to generalize occasion scores over occasions. Regardless where we take a measure, it should produce reliable results. We can also generalize it across raters. If we know that we tested it with a number of raters and we get consistent scores, then anybody can use the scale and will produce the same score. You can give it to any health professional with the basic instructions, and they will score it the same way. But not always happened like that. So we can identify these errors, and we know if there is an error due to rater or interaction between rater and occasion. That is a problem. I think here I will give you a very good example. I did my postdoctoral study in Auckland Med School in Auckland City Hospital. And they did many surgeries, and they actually looked at surgical safety there, and involved me in assessment of surgical safety, because there are many psychological factors what we are looking at that affect safety during surgery in particular. They made sometimes mistakes are made, and people do make mistakes sometimes, and we try to find out what causes them. And we assist team performance, actually having two raters assessing each surgical team simultaneously from two different positions, not talking to each other, but they talk to the teams. When they came, they talked to the teams, say hello, and they were sitting behind the glass and scoring them independently from each other, and then compare results. Everything was fine, and actually they got a very high reliability, inter-rater reliability of 0.8 using classical test theory to measure that. But what's happened when I used G theory to evaluate that, what I found that the major source of error was an interaction between, because we assessed different teams, was an interaction between a rater and the team. That was the major source of error. And we started thinking about it, why it is happening. But for example, if surgeon is a very friendly person, may not be excellent surgeon, but a very friendly person, raters coming to the surgical theater, and they offer them tea and say, okay, guys, hi, how are you? And talking to them and joking, they have a very pleasant perception of that person. And even when they do sort of moderately, they still give them higher score. And depends also on the rater. Some rater likes that surgeon, some other doesn't. And other people are very focused on what they have to do. They're very focused on the surgery. They don't say them anything. They say, okay, we don't have time. If you want, grab a cup of tea and don't bother us. So this team might be a perfect team, but still we've got this bias. Statistically, we identified that bias. What we started doing after that, we said, okay, now raters should not contact the team. They should do assessment without contacting team. They come, they sit behind the glass, assess the team, and then after that, they can talk to them. They can give them a feedback. So you can see how useful G theory can be to identify the things. I would never think that would be a bias. And if you use just classical test theory, you will see that they are very consistent with each other. So then we have a bit of more jargon about facets. So facets, factors influencing measurement, can be crossed and it can be nested. So crossed facets means that every person is present at every level. It's basically repeated measure with one group. If you look at from ANOVA perspective, repeated measures with one group, that is what cross design is. But if we have nested facet, that means, like in our case, for example, raters were nested in the teams, and teams were nested in hospitals, because we assist 3 different hospitals. We worked at 3 different hospitals, and not all raters were the same in the same team. So the raters were nested in teams. So this is more complex nested design. And that happened, for example, if you assess reliability, students can be nested in classes, or patients can be nested in diagnostic categories. So you can look at all these interactions. Example of 2-facet cross design, that is what we use: person, object of measurement, by item, and by occasion. That is how it is expressed in generalizability theory. Usually you use the large capital, the first capital letters. You say P by I by O. Okay. Now how it looks like the same design. It is called 2-facet design, the most popular design. This is how it looks graphically. You can see here is variance of person. Then we have variance of occasion and variance of items. And you have all the interactions here. Interaction between person and occasion, person and item and occasion, and interaction between all 3 of them. And sometimes some interactions are merely 0, but at some you can get quite substantial amount of variance. So what we do, if we define, why do we need to define object of measurement? Because unlike a classical ANOVA, we control for person variance, for true variance here in G theory. So we actually subtract the person variance, the object of measurement, and then we sort out all the errors out of 100%. And that is a principal difference between dealing with everything together, where you always get inflated variance, because a person variance will be present in everything, and you multiply it actually. So creating a bias in estimations. So with G-theory is very accurate about it. We can always identify true variance between persons and separate it. And then the rest, we deal with the rest and try to sort it out between, and recycle if possible, to make these variance components useful for us. And they tell us sometimes a very good story about what's going on in our assessment design, or in our measurement design, or even in our intervention. If you look at intervention studies, you can find many interesting things by evaluating variance components. So where G-theory is applied, traditionally, the way it was applied is observed structured clinical exam, or ASCE. And this is where it is in particular useful. For example, because you have here so many variables, so many potential sources of error. You have students, then you have examiners. Examiners are not the same for every student, because some examiner may go and have coffee or having lunch. Examiners changing. Then you have testing rooms, or stations, they call stations. And in one station, you look at, you use stethoscope to check lungs, in another, measuring blood pressure, heart rate. In some, you need to interpret a scan. So stations are different depending on qualification. But anyway, examiners and stations are changing, and stations are different. So there is an interaction component. And sometimes what's happened, students fail a clinical examination, which is a big issue for medical students, because you spend so much time to study, and it is expensive in many countries. Not in many countries a medical education is funded. So it's a big problem. And imagine two people study together, and one passed exam and another didn't. So they say, who take exam? Well, who was there when you checked the lengths, or where you did, you interpreted the scan? He said, oh, that was Mr. Brown. Oh, I said, that was a lady. I remember was a lady, and he passed. And then they go and complain, of course. And through that complaint, it may cost to the university, it may cost a certain amount of money. So statisticians were engaged to find out how you can deal with that, how you establish reliability of observed structured clinical exam. And unfortunately, it was a generalizability theory available, developed by Cronbach, and they started using that a lot. Generally, in medical education, it is used a lot for that purpose, to establish reliability of high-stake tests. That is where it is used. And now we started moving to other areas and develop new methodologies based on G-theory, because it can answer many research questions we are unable to answer using classical test theory. So look now how observed structured classical clinical exam looks like. You have, for example, 200 medical students. Can be nursing, can be dentistry, can be general practitioners. And you have 10 stations. In one, you use stethoscope to check the lengths. Then you can, in another, you need to look at CT scan and interpret if there is a tumor and evaluate that. Then you need to interview an examined patient, for example, complaining for abdominal pain. So one examiner per station, and assessing student on a scale from 1 to 10. And it includes both. It includes competence and safety of practice. So there's two components in that 1 to 10 assessment score. So the G-theory can tell us now how much variance is here due to student, how much variance is due to station, how much variance is due to examiner, and all their interactions. So the power of G-theory is to estimate each source of variance to distinguish true difference between students from specific sources of error. So once we identified of sources of error, we can establish a coefficient which can tell us whether we can rely on that assessment or not. And what's happened usually, you have a certain design, you try to maximize number of examiners and collect data. And then without doing more experiments, just having that data, we can do it in a lab, we can manipulate design. In our software, we can actually remove examiners from different stations. We can manipulate number of stations, number of examiners, number of students, and try to optimize measurement to find out at what stage we can get a reliable score, where we can reduce errors. And that is very powerful because without doing many assessments, you just need to collect data once. You can find an optimal way to do this, to conduct this examination. And that's what people did. And now examination is reliable where G theory was used, apparently. So what we do, we calculate variance component for each facet first. And then, more important, we calculate an interaction because you can imagine a student can be it's just a gender factor can play a role here, very obvious. So student can be male or female, and examiner can be male and female. How do you know if there is an interaction or not? And then student station, some students maybe, or maybe majority of students in that particular course are better on some specific skills and worse on another skills. So we need to see how students interact with stations, whether there would be actually an error. And then you have, of course, a larger interaction between student, examiner, and station. So particular examiner and specific station can make things better or worse, right? So I hope you follow what I'm saying. Now we come to the main coefficient, what we use in generalizability theory. It is called G coefficient or generalizability coefficient. The coefficient is nothing special in the sense that it is a value from 0 to 1, the same as Cronbach's alpha, the same as test-retest. And in terms of interpretation, it's also very similar. But the difference is that this coefficient encompasses or incorporates all and considers all sources of error in your measurement. And there are two types of them. So basic definition of this coefficient is a ratio between observed or true variance of our object of measurement, in this case persons. So true variance between people on particular assessment instrument, let's say personality, neuroticism, for example. We measure neuroticism, and the true difference on neuroticism between people is our true variance, okay? And then it is a ratio to the total variance, which includes all sources of error we can identify in our measurement design. G coefficient of 0.8 and higher indicates good generalizability of scores across situations and occasions if you have these facets in your measurement design. And this is a very basic formula of G coefficient if you are measuring trait, so variance of persons, and then you have total variance including error. We have two different G coefficients. One is relative and one is absolute. A relative G coefficient only looks at sources of variance that affect our object of measurement directly. For example, we look at person variance. So person occasion interaction and person item interaction would be, and person item occasion interaction, these three will be direct sources of error affecting person, right? While items alone and occasions alone are not direct. So we never consider them if we do test-retest reliability score. So in here, in relative coefficient, but it is very important because this actually includes all these interactions here. We can assess relative measurement. And generally, people use relative G coefficient to assess reliability if we use G theory. However, if we need higher precision, what we do, we look at all sources of error. And with all sources of error, we have our direct or relative error variance, and we add to that also variance of occasion, independent of anything, item, and item-occasion interaction. So this way, we can get the total error variance, and our G coefficient, or absolute G coefficient, is the most robust measure of reliability available in statistics today. So I did a search, and I always check what is coming up, and I haven't seen anything more accurate than that, because of course this is related to a person item occasion design, but in more complex designs you can have very long chain of interactions. You can put everything there. As long as you have data, you can keep adding. You can keep adding interactions and sources, unless the only problem is that you may not have enough power to cope with a number of variables. So you need to increase sample size, probably, number of assessment occasions. But with this design, you don't need a large sample size. This design will work wonderfully with just 80 people, assessed 3 times. And you will get very high generalizability of, by assuming there is not much error in your scale or items or occasions, okay? So the delta, sigma with the delta, it's a total absolute error variance. It is called sometimes also phi coefficient. So how we conduct analysis, now we come to a bit more practical way, because if you're interested to do this, so there are 2 major analyses you do by applying generalizability theory. The first analysis, what you will be doing, is called a G study or generalizability study. The generalizability study is a sort of a diagnostic. Like if you go to, for example, if you go to GP and get a check, you don't know what the problem is, but you just go and get a check. That is a check of G theory. You have your data, and you scrutinize your data of your assessment instruments and around a G study. So the G study will tell you how well you can trust your measurement. And here you will produce G coefficients for your scales and subscales, and you can see how much error is attributed to different components and their interactions. So it accounts for object of measurement as a major difference between traditional ANOVA using classical test theory and G theory. So we always keep our true variance separate, not to avoid inflating actually variance of our error or our interactions. As if person comes in every interaction, you will get huge amount of error variance, which is not true actually, because the true variance is 1. So once we conducted a G study, I think I have, no, I will have an example later on. We do a D study. D study is a decision study. In a decision study, we actually decide whether the scale or a measurement design what we're using to assess something. Whatever it is, clinical examination, or we are assessing different raters on a sport competition. It could be anything, but we look here at the design, whether the design what we have produces a high reliability, high enough to make fair judgment, right? So in this case, we will manipulate with measurement design. We take original measurement design and we can remove different levels. We can remove facets, we can remove raters and see what's happened. This is an experimental part of G theory, is the most exciting one. Because by doing this, you can see, you can evaluate every single symptom in psychopathology. You can look at every single symptom of anxiety, of depression, of schizophrenia, of autism, and see whether this symptom, to what degree this symptom is dynamic or stable over time, depending on your research design. And of course, it is very useful. Amendable symptoms are easy to change using interventions. So you may decide to make them the first target of an intervention because they are more amendable. While very stable symptoms are hard to change, they are not changing over time. And so they can be used to evaluate potential risks, to estimate sort of risk groups, or to predict risk to develop a particular condition. So if somebody is high on particular stable symptoms, that in certain circumstances can lead to psychopathology. So this study is a very important component here. So you always do two of them. First G study and then D study. If you're happy with the results of your G study, actually, there is no need or no point to do a D study sometimes. If you know that you are measuring trait, for example, and you're sure it's a good measure, you check it and you get expected coefficients of 0.8 and higher, you can keep going with this. And this is what's happened when people analyzed a big 5 personality in the US with a large enough sample. They found all G coefficients, all relative G coefficients close to 0.8. So, and they stopped there. They still played a little bit with this study just to show that you won't get anything better than this. Sometimes we need to provide evidence. We need still to do something to show that you won't get a better result. Okay. Now, steps. Following, if people giving workshops, well, I've attended several workshops myself, and it is expected to have particular steps there, how you do analysis. Let's say you started doing generalizability theory analysis. What are the steps? What should you do? For the first, there are 4 sequential steps, main steps. The first step is defining measurement design, because without that, you don't know how to program. The software is not like a species or R. So usually the software we're using for generalizability theory, you need to, every study, you need to design your measurement. And for a simple measurement, it's not difficult. But if you start designing nested, you work with nested design, that becomes a little bit more problematic. You need to be very clear, what are you measuring, what is nested in what. So in this case, you program it with separating person, subject of measurement, and having item and occasion as 2 facets. And the next step, you compute variance components using traditional ANOVA. Of course, if you use EDAC-G software, what I will be discussing in a few minutes, then you will get your ANOVA, traditional ANOVA results together with G study results. You just need to tick the box. But traditionally, these are 2 steps. And also in computational sequence, there are 2 steps. If you compute variance components using traditional ANOVA, all variances come inflated. So you'll get person variance in all interactions. The numbers are huge usually compared to what you have after you remove person variance, a true variance out of it. So then what you do in G, this is exactly what you will be doing in G study. In G study, controls for person variance, for your true variance, remove that and estimate G coefficients and evaluate sources of measurement error. You will get variance components and you get them in percentage, which is a great thing because variance component is hard to compare otherwise. If you get your error sources out of 100, you can evaluate them very simple. You can see, for example, if you have 60 or 70% of variance due to person-occasion interaction, you can say the scale is measuring, probably is measuring state. But then you need to test this hypothesis to compare relative ratio, to compare person variance and variance due person-occasion interaction. See what's happened there. And if you will get a dominated variance due to person-occasion interaction, you can say it is a state measure. It has nothing to do with trade. But you need to have this to base your conclusions on numbers, on exact numbers and ratios. So once you know the situation, your diagnostic in G study shows something or tells you something important about your measurement, the next thing you do, you will play with your data. And this is a good fun. So in this study, you can do all different things by removing different facets, reducing levels, and see what's happened. And examine your measurement and sources of variance. Okay. These are definitions for cross-design what we are discussing. The classical one, person, item, occasion for psychometric. Here are just definitions of person, item, occasion, and interaction variance. I put it in words because I think it's easier to understand than putting formulas everywhere. So because that tells you actually how it is calculated, how person variance is calculated, and how other variances are calculated. Now that I want to mention this study because this is important, one of the pioneering studies using G theory in psychometric, only conducted in 2014, but it gives us a benchmark for trade. So because personality in Big Five personality inventory, we assumed that personality is stable, but until that study, there was no robust evidence about it. We only have had this assumption, and this assumption was merely based on test reliability scores, which I will show you why it is unreliable again on different examples. So reported G coefficients for each subscale, what they found, and relative ones, were from 0.8 to 0.9, and supported validity of that measure. But they didn't do individual item analysis. I assume that there might be some individual items more sensitive to changes over time. But if you put many items together in a measure, sometimes these variants due to state, these variances, they cancel each other. That's happened similar to signal averaging in EEG. If you average signal across different measurements, it shows you P400, P300, etc. It's a very nice curve. But if you just look at one assessment, it's so messy. You can't recognize anything there. The same thing happened if you imagine your different assessments are different items. With one item, you may have a lot of variance. With other items, less variance. But if you put them together, some error variances cancel each other. And what you have at the end, most of it is just your trade. This is true for most of the trade measures. For state measures, it's not the case, because for state measures, you will never actually get a stability. Even if you combine items, you will still get a lot of variance due to person-item interaction. Okay, so this is how it is presented. You have a G coefficient here. That is the relative one. They call it just G coefficient. And this is an absolute one. They also calculated an absolute one. And for absolute, you can see the lowest one for openness is 0.75. This is very high, given that absolute G coefficient take into account all sources of variance, direct and indirect. And now, here, what they did is manipulating measurement design and reduced number of items. And you can see what's happened. If you only have one item, and one occasion, your generalizability coefficient is merely 0.45. So it's less than chance. With two occasions, you get 0.52. With three occasions and one item, you get 0.55. But if you start adding items, you will get effect of signal averaging, similar to that. By adding items together, it improves. And you can see why in factor analysis or in any assessment, when we construct psychometric measure, we always want to have at least 3 items, right? It's clear, you can see it from here, because with 3 items, you get more or less acceptable reliability. With anything below 3, it's hard. But ideally you would have 5 or 7 items per subscale in a measure, because otherwise you will get a lot of error. I will go in terms of time. Okay, now importance of distinction between state and train. In psychological or biological interventions, we usually, working with psychopathology with patients, we aim at trait changes. Because if we only change a state during treatment or during therapeutic session, relapse is inevitable. Let's say you do an intervention, and during intervention, because people working together, doing some mindfulness exercise or whatever they do, or they have progressive muscle relaxation, or they undergo some other treatments, some alternative treatment, while they work in group, in that time, their state may be changes. But after that, 2 weeks after the intervention, they may relapse and go back to their baseline level of depression and anxiety. So we want to ensure that it is a stable change. So that is a reason. Another one, effectiveness of any treatment can only be evaluated using state changes. So you measure actually a state before and after exercise. Also useful to identify conditions in the environment that support psychological treatment. For example, in specific environment, a state anxiety can be lower. So you may promote lower state anxiety or lower state depression. You can identify those environments and create these environments artificially. You can select participants for neurophysiological studies based on trait scores. So you can't rely on state scores, right? And because states and traits are always confound, we have problem in assessment. So with test reliability, we had this criteria established by Spielberger, who developed the famous state and trait anxiety inventory. What he said simply that everything below 0.6 is state on test-retest correlation, and everything above 0.7 is a trait. But the items are changing. You may have higher score on one item and low on another one. You won't get any difference over time on the total score, and the correlation can still be 0.8, but there could be a huge difference in terms of symptoms people experiencing. In particular, if somebody goes low on appetite, but at the same time go on disturbance of appetite, but go high on suicidal ideation, the score is the same on depression, but the difference is huge. Somebody can maybe already staying on the roof, and we need to do something, but our scale is not showing that. So that's a good example of that. So that is where we validated this method using mindfulness state scale, because we didn't know it is a state, because people claimed it is measuring state. So we took a scale which is called Toronto Mindfulness Scale with 55 people, and we manipulated environment a little bit. So the first assessment we did after holiday, when they just came after the holiday to the university. Then we assist students after mindfulness exercise. We run a recorded mindfulness exercise during class. And then just before an exam, we talk to the class regarding exam questions, and we ask to actually to respond to items. So this is to increase variability of the state, because we want to see if there is a variance. Without that, you cannot evaluate the measure. You need to expose measure to high variability. So what we found that in this measure, we found with all good Kronzbach alpha coefficients, and test-retest, traditional test-retest was quite low over time in classical test theory. And this is what actually traditional ANOVA shows. You can see here inflated variance components, because it accounts for person all the time. Here in percentage of corrected. you have person-occasion interaction still is the highest component, indicating it is a state measure. But you have person, occasion, and item almost the same amount, which disappears if we go into our G study results. Here, 90%, 90.9 is person occasion. So it is a pure state measure. Only a small amount of variance is attributed to person. And here we have almost 100% in decentering scale, almost 100% of person occasion interaction. This is a very good measure of state. And by doing that, we developed coefficients to measure state, to distinguish state and trait as a ratio. The state component index is a ratio of variance due to state to the variance state plus trait. It's a very simple formula, but it gives us very reliable coefficients to distinguish between the two. And we use that a lot since then. In particular, we found these two items enter onto mindfulness scale, which are very, very sensitive to state changes. They don't have a trait component. And if you think about it, experience my thoughts more as events than as reflection, this question has no personality really. If you would be in that state, it won't depend on your personality level, because it has no personality component, essentially. And it changes all the time. People can be like that at some moment and not at another moment. So these state items do exist. I thought they never exist. I thought that state items should always have a person component, but we found two, which apparently have only negligible trait component. They merely state. So this is a study we did recently on quantifying schizophrenia symptoms, applying generalizability theory in clinical trials using traditional person, item, and occasion design. I try to wrap up because I think we run out of time a little bit. So I will just mention that study and the literature. So what we found that a scale, a traditional one with 3 factors, has a high reliability over time compared to 5-factor model, for example. You can see all relative G coefficients here close to 0.8 and higher. And state components index is lower. So if you think to use that, you better use a 3-factor model or the total score. Total score is the best. It produces very stable characteristic. But we also identify dynamic symptoms and stable symptoms. These are the most stable symptoms of schizophrenia, like poor attention, blind affect, delusions, poor report, mannerism. These are the most stable ones. While dynamic ones, where more than 40% of variance is attributed to dynamic changes, include, for example, disturbance of volition, grandiosity, preoccupation, motor retardation, uncooperativeness, and lack of judgment inside. Also, hallucinatory behavior, what we know, is actually very dynamic. People can have it at some stage and cannot have it at another. Guilt feeling is also, and somatic concerns are also in time. So this is how it can be useful. And I think here is some work what we've done with surgical safety, applying generalizability theory to evaluate surgical safety checklist, distinguishing between enduring and dynamic concussion symptoms, investigating stable and dynamic aspects of students' motivation, evaluating state and trait aspects of perceived stress, examining state and trait symptoms of anxiety. This is under review now. So quite a few studies, and we even looked at memory tests where you use the same materials. In some memory tests, for example, in the cognition memory test, you need to use different stimuli over time. You cannot use the same words, for example, for pre and post test, because there would be a learning effect. You need to use different words. How we know that this test is reliable? So we use G-theory to find out how many words do you need overall and how many trials to get high reliability. So generalisability theory can be useful. I'm wrapping up now. Can be useful and applied to distinguish between state and trait components. So one of the most appropriate methods today, there is one latent state and trait model to distinguish state and trait. But the problem with that model, that it is not simultaneously assess reliability of measurement and other variance components. What G-theory does, and it has an advantage. And it can be used to any area of measurement, in psychometric measurement in particular. Pros and cons of G-theory. It's a major advantage over classical test theory. Powerful to assess reliability. In particular, you can look at single items and instead of total scores. Can tell us how generalizable our results are from our sample to the wider population. Disadvantages requires a good statistical background of friendly statistician to help you. Software more challenging, and it is underused. So thank you for your attention. And here some references on my presentation.
Brilliant, thank you, Oleg. I'm going to unmute everyone now so we can give Oleg a round of applause.
Yeah. I think I can probably stop share or
that's brilliant.
Share. Yeah, and I look at the
very
chart.
Interesting, very interesting talk on a very powerful psychometric tool, Oleg. Before we have a couple of questions, in particular from Saeed, and Saeed was wondering, a lot of anomalies in experiments or measurements can affect the overall variance. So if you have a mismeasurement in your data, is there any clear methodology to exclude them, and preferably automatically? How does G-theory handle those outliers?
Well, if you collect data from the beginning with repeated measures, you can scrutinize it using G-theory, and you will see what points of assessment you can exclude, for example, which are unreliable, which produce your error variance. You can actually establish generalizability coefficient from the existing data and remove those points which are unreliable. You will see experimentally, you will need to do a D study for that. So start with G study and see if your G coefficient is low overall. So you want to improve it. Right, so you go and conduct a D study, and in this study you can manipulate levels, and you may decide to exclude a particular assessment occasion which creates most of the error. And it is very microscopic, really. You can look at every tiny source of error and evaluate it out of 100, how much it brings you. And you can see very interesting things. Of course, it is possible, yes, but you need to do you need to plan your measurement design from the beginning so it will be compatible to G-theory assessment.
That's great. And so you can do that on the item level, or you can do it if there's a person who's an outlier. If a person has a number of trials, you can do it as a trial as well. So you can look at it at any level of the data.
Yes, absolutely. You can look at any level. You can look at person, you can look at item, you can look at occasion, you can look at interactions as well.